Okay, guys, welcome. Today we're going to talk about the law of large numbers, and we'll also talk about the law of small numbers and the law of very large numbers. Okay, so for the law of large numbers, we're going to start with a motivating example. Okay, and we'll carry this throughout our discussion on the law of large numbers. Now, we're going to consider tossing a coin n times, right? And of course, the idea is that each coin toss is independent of the others. Now, just to make things simple, we're going to let n be an even number, right? So we're tossing a coin some even number of times. Now, of course, every outcome is going to be a sequence of length n, where each element is either h or tails, right? So if you're tossing a coin n times, you have this string of heads, tails, heads, heads, tails, 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 something like that, where there are n of these things, right? That's all we're saying here. Now, the law of large numbers says that if we toss a coin many times, the number of heads will be about the same as the number of tails. Okay, now that's sort of putting it in layman's terms. Now, can we be more precise than that, right? And of course, we also need to account for extreme results, right? We can be confident that the number of heads and number of tails will be about the same. But of course, there are extreme cases where this may not happen. Now, we could maybe make this a little bit more precise by saying something like flipping a coin n times, the probability that the percentage of heads is between 49 and 51%, that probability will approach 1 as we make n increasingly large and send n off to infinity, right? Now, 49 and 51 aren't special, right? We could essentially make 49 and 51 as arbitrarily close to 50 as we want, as long as 49 gets close to 50 from below and 51 gets close to 50 from above. So the simplest form of the law of large numbers can be stated something like this, right? So we're going to fix an arbitrarily small positive number epsilon. Okay. Now, if we toss a coin n times, then the probability that the number of heads, right, which we're denoting here probability of A, is between 0.5 minus that arbitrarily small number epsilon and 0.5 plus that arbitrarily small number epsilon. The probability that our number of heads is between that, or that our probability of heads is between that, is going to approach 1 as n goes to infinity, right? So what does it mean for a probability to approach 1? It means that you're approaching that it's guaranteed to happen, right? Now, a related theorem, at least in this case, is going to look something like this. So now if we let t be between 0 and m, then the probability that out of 2m coin tosses, right, which we were letting n be here, the number of heads is less than n minus t or larger than m plus t, is at most equal to this, e to the minus t squared over m plus t. So with this in mind, how large should n be so that the probability of heads is between 49% and 51%, with at least probability of 0.99, right? So here's the idea. We would want m minus t to equal 49%, right? And we want it to equal 49% of n, which is 2m, right? So of course, we can solve this equation, right, for t. And if we do that, what's really happening here is that we have that m minus t is equal to a 2m times a 0.49. And if we solve for t, what's going to happen is we're going to get that t is m over 50, right? So that's sort of the idea there. Now, by the previous theorem, we know that the probability that this is not in this range is at most this, right? Now, if we plug in what we know, we can handle the exponent because we said that t was m over 50. If we plug that into here, we'll eventually find that this exponent is minus m to the 2550, right? So we want this probability to be less than 0.01, okay? So if we wanted this to be less than 0.01, you could use logarithms or a calculator, but solving for m would give you that m would need to be at least 11,744. So you need to toss a coin 11,744 times in order to ensure that the probability that your proportion of heads was between 49 and 51% had a probability of at least 0.99, right? So that's sort of the idea. Okay. Now, of course, many times we don't need to be this certain, right? And a lot of times in, for example, if you ever take a statistics class, usually the percentage that you're going to go for is 0.95, right? So now let's suppose we want the smallest interval possible that would give us a probability of 0.95, right? So in other words, we want the smallest t possible that e to the minus t squared over m plus t is less than 0.05. Now again, you could solve this for t using calculators and logarithms, and you can eventually show that if t is 2 square root of m plus 2, that would make this less than 0.05, right? And that's something that you should verify on your own. So now, of course, if t is 2 times the square root of m plus 2, right, then we have m minus t and m plus t right here, right? So with probability of at least 0.95, the number of heads among two m coin tosses is between these two values, okay? Now that's the law of large numbers. Now we can also talk about the law of small numbers and the law of very large numbers, right? And these are sort of extreme cases. Now the law of small numbers says that if you look at small examples, you can find many strange or interesting patterns. And of course, the danger of looking at these things is that they do not generalize to larger numbers, right? So just as a silly example, you could say that every odd number is prime, right? Which of course, if you look at just the odd numbers from 3, 5, and 7, right? Of course, it's true in that very small lens, but as soon as you get to 9, that fails, right? And of course, 1 would also be not prime as well, right? 1 is kind of not prime or composite. Right, because the definition of prime would be circular for the case of 1, right? So 1 in itself, well, itself is 1. So what does that mean, right? Now, a more interesting example is that if you look at n squared minus n plus 41, the claim is saying that that would generate only prime numbers. Now, if you try out numbers until you get to 40, this will work, right? If you plug in 0, 1, 2, all the way up to 40, you will get a prime number to come out. But as soon as you enter in 41, then you get 41 squared minus 41 plus 41, and of course these would cancel out, and you would get 41 squared, right? So of course, once you hit 41, this is not true. So in conclusion, what the law of small numbers is saying is that you could get these results that seem that if you look at a small enough sample, that you have something that would hold in general, right? But of course, this law is basically saying to us that if we want to prove a mathematical conjecture or statement, it's not enough to just observe a pattern or rule, right? Because you're only looking at small instances and coincidences are bound to happen. So you need to use some sort of rigorous proof to justify things like this for all cases, not just for a number of cases that we could observe. Okay. And then, of course, the law of very large numbers says that the same thing can happen for large sets of data as well, right? But we try to use different types of results, sort of like what we looked at for the law of large numbers, in order to make rigorous proofs about statements as well. All right. So that concludes this video on the law of large numbers. I hope you enjoyed, and I will see you next time.